Well, hello and good afternoon. Welcome to the third Joint Institute of Physics and German Physical Society panel event. Absolutely delighted to welcome what I think is going to be a really lively discussion. My name is Tom Grinier and I'm the CEO at the Institute of Physics. This is my first event crossing between the IOP and the DPG since joining in the summer this year. This series was established in 2020 during the pandemic, when the IOP celebrated our 100th anniversary jointly with the DPG, who celebrated their milestone of 175 years. The event in 2020 focused on climate change and started a really fruitful tradition of collaboration on this series between our two organisations. Together, we've recognised the importance of having two perspectives from the UK and Germany, both what brings us together and what may be different, and looking at why that might be and what we can learn. And I think that really represents to me the benefit of bringing these different points of view together to discuss the current global challenges and the role that physics plays in helping solve them, while also highlighting the benefits of a multidisciplinary approach to tackle these challenges for the benefits of society. We really hope our collaboration will continue to serve the interests of the physics community and beyond, and we really would be delighted to hear from the 150 of you who are currently tuned in at the moment about what topics you'd like to see us cover at the next event in 2023. There's going to be a short poll at the end of the webinar to collect your thoughts about where next. But turning to this year's event, as I've said, we're expecting a lively discussion. Volatile energy, how do we solve the long-term storage problem? I'm sure you'll all agree this is a crucial question in trying to manage the transition of our energy system from fossil fuel-based production towards fossil fuel-free production. I'm not going to steal anybody's headlines, but I do know that our panelists have got some really interesting thoughts that they want to share with you. So to begin the discussion, it's now my great pleasure to introduce the chairs for the event today. First of all, Karl-Friedrich Ziegahn is chairman of the Energy Working Group at the DPG, as well as being a member of council and on the advisory committee on science and communication, and is a KIT Distinguished Senior Fellow. He formerly served in an executive position as a member of the board of directors at Karlsruhe Institute of Technology and head of division of the Natural and Built Environment, responsible for faculties on civil engineering, geosciences, environmental sciences, and architecture, as well as research programs on renewable energy, energy efficiency, and atmospheric climate research. From 1980 to 2006, he researched with the Fraunhofer Society and has a strong background in environmental engineering, energy and automotive technologies and material science. He holds a diploma in physics and achieved Doctor Ingenieur both at the former Technical University of Karlsruhe. We also have with us from the UK, Shanta Noray, who is a member of the IOP's Energy Group and Principal Scientist in the Energy Materials team at Ceres Power Limited. Ceres Power is a fuel cell technology and engineering company whose aim is to bring cleaner and cheaper energy to business, homes and vehicles. As an expert in microscopy, materials analysis and spectroscopy, Dr. Ray works with his team across multifunctional teams and the companies to advance innovation, development and improvements of metal-supported solid oxide cells. He has more than 20 years of material science and surface analysis research experience in academia, governance and industry sectors. He leads multiple projects in improving the efficiency of fuel cell interface and chemistry. So I think you can all agree we're in really safe hands with two expert chairs to set up this afternoon's debate. Over to you.
Sorry, I was a bit late to unmute myself. Thank you, Tom, for this very kind introduction. And I would like to thank you all, my colleagues here in the panel, and also the participants to joining us this evening. I will not speak too much about DPG. This is a very large organization of physicists, and we have some 55,000 members, which probably is the largest organization of physicists in Europe. We have a working group on energy, and it's not surprising that many of our members are interested in the topic of energy. So we have roughly 2,000 members of the working group on energy, and you may imagine that this is not, let me say, easy to handle. We do annual meetings, we have conferences, and we exchange a lot of knowledge. And we always invite people outside physics to join us and to explain us, for example, chemistry or engineering science, but also legal science is so important. What is the politics doing in the boundary condition for energy development? That's in a nutshell the activity of our DPG working group. We have organized this event in a discussion, in a preparation group, and we found out that one of the most important challenges is during the transformation towards fossil-free energy delivery, and fossil-free, let me say, means mainly based on what we call renewable installations, wind and solar and geothermal and all the and tide and ocean energy. What we need is a baseload capacity, and baseload capacity means that we need energy storage, and not only for hours, but also an energy storage capability for weeks and months. And therefore, we have chosen this topic on the long-term energy storage, and we would like to discuss this topic this evening briefly with our panelists. We have an update on our participation this evening. Unfortunately, Christina Roth is unwell, and her place will be or her position will be given by Ulf-Peter Apfel. And I will in a minute give a short introduction about our panelists. There is a chance, I should point out how we work this evening. We are limited to 1.5 hours. There's a chance to ask questions after the panelists have given their, let me say, initial statement. You can use the question poll to vote on which question you would like to have answered. And it's my invitation to you is, please ask question by typing it into the question and answer box. You can find the question and answer box on the baseline of the screen, and you can typewrite your questions in it. We will follow, Santana, my co-chair, and myself, we will follow these question and answer boxes, and we, as I suggest, we should have a lively discussion. Don't be too shy to ask the questions. We will probably have too much questions. We cannot handle all of them within this session, but I'm happy that the panelists are willing to share their email addresses with you. So if you have a specific question, you can, and we cannot discuss the question here, you can email it to our panelists. So that is my short introduction. Please, Santanu, it's up to you now to continue. Thank you.
Thank you very much, Karl, and thank you very much, Tom, for my introduction too. I am Shanta Noray, a co-chair of this event and a member of IOP Energy Group. Now, as Karl said, the DPG is quite big, and IOP is not big, but we have big aspirations, and we have about 24,000 members at this moment. And I'm representing today IOP Energy Group, and just quickly a little bit about IOP Energy Group. It is a special interest member-driven group. We are interested in different topics, including but not limited to the efficient use of energy, materials for energy applications, optimizations of energy use, etc. With more than 30% of our members involving students and academics, our membership include people from different sectors of energy. With financial support from IOP, our group gets involved in organization of different events and conferences involving energy and efficiency. Now, as rightly Karl mentioned, we have chosen the topic today because energy storage is one of the biggest global challenges that the world faces today. On the back of COP27, we wanted to highlight the solutions that are available that will change the landscape of long-term energy storage, production, and transportation. So these are really important points, and this is really high time, or if not a bit late. The importance of making energy storage green is necessary to ensure we can fight climate change, and this is a challenge that we must all engage with. So these are the few reasons, and also, as Karl mentioned, that why we chose this topic. And the Institute of Physics and German Physical Society have brought together 4 expert panelists who are leading the way in technologies that meet these few objectives that I have just mentioned and Karl mentioned earlier. Now, 2 panelists are from the UK and 2 panelists are from Germany. Now, it is with my great pleasure that I introduce the panelists from the UK. We have Nick Lawrence, Director of Advanced Engineering at Ceres Power, and my colleague, and who has got 25 years of experience developing technologies across the automotive and energy sectors. He has led projects developing both high-speed racing and fuel-efficient internal combustion engines, and he joined an energy storage startup as chief engineer to develop a novel long-duration thermal energy storage system. He then joined Ceres Power as head of mechanical engineering, where he grew and developed the mechanical engineering team over a period of rapid expansion. Nick now leads all R&D activities for novel stack and systems, including partnership with RFC Power on developing a novel hydrogen manganese flow battery energy storage system. Thank you very much, Nick, for being here. We also have Professor Jihong Wong, who is the head of Power and Control System Research Laboratory at the University of Warwick. Our research interests include power system modeling and control, compressed air energy storage, that is CAES, and its grid integration, energy efficient actuators, and optimal control method. She started working on the research topic of CAES from developing the world's first compressed air uninterrupted power supply in 2005. She led the EPSRC Grand Challenge Program in energy storage from 2012 to 2018. The project obtained a clear picture of the UK underground storage capacity for CAES and conducted a comprehensive study of CAES system energy efficiency improvement. Our research group has recently established a campus energy system living laboratory, which uses live data via an IoT platform for studying optimization, planning, and design of multi-vector local energy systems with integration of energy storage. And so thank you very much, Jihong, for being here. And now I hand it over to Karl to introduce our panelists from Germany. Please, Karl.
Thank you, Santanu. And it is my pleasure to introduce the panelists from Germany, Professor Ulf-Peter Apfel from the Ruhr University in Bochum, and as well working with the Fraunhofer Institute Umsicht, and Dr. Achim Schaadt. He is with the Fraunhofer Institute for Solar and Energy Systems. Ulf-Peter received his PhD from the Friedrich Schiller University in Jena in the field of H2 formation, and I jumped to today's position because you all can find all the CVs and bios in the internet, so we have time for our discussion later. He holds a professorship today at the Ruhr University in Bochum, and he is now leading the department Electrosynthesis at the Fraunhofer Umsicht Institute in Oberhausen. His research interests are in the field of technical electrochemistry, with a special emphasis on the electrochemical reduction of CO2 and protons and catalyst design. Achim Schaadt is head of the thermochemical process department at the Fraunhofer Institute of Solar and Energy Systems in Freiburg. He is a chemist by training and holds a PhD from Kaiserslautern University. And his work includes also techno-economic analysis and life cycle assessment. sector analysis, synthetic fuels and nitrogen, as well as market and industry analysis of the solar energy technologies and other renewables. And he is also, which is quite important, the co-author of the Fraunhofer Hydrogen Roadmap for Germany. I thank all the panelists all together, all four panelists, for joining us today, and will now pass over to them to introduce their activities, their research, and let me say their most important statement, why they are participating and what is the message they want to deliver today. So we start in the rank order with Nick. And Nick Lawrence, it's up to you. Please feel free. We have agreed that we all are very brief in our statements, that we have enough time for a later discussion.
Thank you very much, Karl. And yes, hi everyone. My name's Nick Lawrence, and I'm super excited to be on this event today and to discuss long-term storage. For those that you don't know, Ceres Power, we're a developer of electrochemical technologies for both fuel cells and electrolyzers, and we've been doing this probably and maturing our technology for nearly 20 years now, having been a spin out from Imperial College in London. We follow a licensing business model, and we typically like to collaborate with world-leading companies like Bosch in Germany, Weichai Power in China, and Miura in Japan, and others too, to really deliver clean energy at scale and pace. And I think that's one of the things I wanted to just highlight is that, and Santanu mentioned it too, that the challenge here, the size of the problem is immense, and somehow we need to work together and collaborate to solve that problem. The numbers are huge. The numbers are huge around what we need to store, and we somehow need to work out how we do that best across borders, across countries, so that we get to a solution with a stable net zero position. And we realized at Ceres we really couldn't do that on our own, so that's why we partner with others. And I suppose for those that don't know about our technology, I suppose we like to think of it as a bridge. Electrochemical technologies are always a bridge between something that is an electron and something that is a molecule, and our solid oxide technology is one of the most efficient bridges you can make between electrons and molecules. So if you do have a green electron, first you must think, how can I use that green electron first? Because it's better to use it than to store it. If in a long-term energy storage scenario you do need to store it, then using our technology is a really efficient way of doing that. Most solid oxide technologies convert from electrons to molecules at a really high efficiency. But because our technology is metal supported, it's extremely robust too. So that makes it a really interesting proposition for converting from electrons to molecules. And I suppose the two areas that I'm involved with a lot at Ceres are firstly the electrolysis side, where we're looking to, we're developing a 1 megawatt solid oxide electrolyzer system. And I suppose this is a really good example of where efficiency can really benefit us in terms of the energy transition. If you have some industrial low-grade heat available, you can inject that into a Ceres solid oxide electrolyzer, and you can get conversion efficiencies between 85 and 90%, which is great, especially if you consider the costs for electrolysis. 2/3 of those costs are usually the electricity going to that electrolyzer. And then on top of that, because it's a high-ish temperature, 600 degrees C, there are also some really good thermal integrations you can do. So we're looking at seeing how we can then integrate that with green methanol and green ammonia, which are all really interesting concepts in terms of long duration or long-term storage. The other area that I'm involved with is a partnership, which it's really exciting. It's a joint collaboration with a spin out from Imperial College called RFC Power, and we're working with them to help them develop a novel hydrogen manganese flow battery solution for energy storage. And I think flow battery technology in general is fairly mature, But this is a really exciting one because it gives ultra low cost solution, because it uses manganese rather than other chemicals used in other flow batteries, which potentially could be an order of magnitude lower in cost per kilowatt hour in terms of the electrolyte cost itself, but still keeping a high round trip efficiency and a high power density. And I suppose that's the message I wanted to finish on, is energy storage is very much a tale of scale and cost. And somehow we need to keep the technologies and scale the technologies where it is really cheap to store and efficient to store. So if you can store cheaper than it costs to throw away the energy, then you will store it, and then you will have that available at a future point in time. And I think that's all from me. Thank you.
Thank you very much. And I think we will get enough questions on that. We decided to have all these short statements before we start into the question and answer session. So we have not yet a discussion or question, and we continue with the next presentation, which is given by Achim Schaadt, or presentation or statement or introduction. Achim, please.
Yes, thank you very much. Good evening from my side as well. Hopefully you should see my screen with a slide. So it's about hydrogen and sustainable synthesis products and their role in the energy system transformation. I would like to talk a few words about it. Let me first introduce the Fraunhofer ISE.
Sorry, Achim, we don't see your slides. At least I cannot see your slides.
Oh, I'm sorry. I will share it again.
Share your desk.
Okay, sorry for that.
That's the normal mystery situation, which we always have in online conferences.
I will share it again.
Just to give it to, yeah, here it is. Perfect.
Here we go.
Yes,
Oh,
you should
okay.
go in the presentation mode that you get the slide larger.
Okay. Do you see now the presentation mode?
Perfect.
Okay. So sorry for that. So it's about hydrogen and the sustainable system synthesis products and their role in the energy system transformation. Just a few words about the Fraunhofer ISE. It's in Freiburg, the southwestern part of Germany, and it's we are about 1,400 people working on this topic. You see on the right-hand side. So it's about photovoltaics. That's half of our institute, and I'm in the division Hydrogen Technologies, and this division is headed by Christopher Hebling. And we cover a quite broad range of hydrogen technologies, from the fuel cell systems to chemical energy storage, with Tom about electrolysis. But in my department, it's about thermochemical processes, which I will talk about today. And here are some information about our work. It's about Power to X products, the production, the transport, and the utilization. So we cover the whole Power to X value chain, and we focus specifically on power to methanol and the methanol to X products. So we developed technologies for DME, dimethyl ether, oxymethylene ether, and also methanol to jet fuel is a topic in our department. And on the right-hand side, so we have also technologies related to direct air capture, DAC, and several hydrogenation, dehydrogenation technologies. It's about ammonia, of course, and direct electrical heated catalysts, also for ammonia reforming. So quite broad topic, but it's connected. But it's about catalysis and technology development, and this is covered by this techno-economic assessment and life cycle assessment. Regarding expectations and the demand of hydrogen and synthesis products, we made last year a study for the National German Hydrogen Council, and the clear message was that it's that hydrogen and synthesis products are needed. It's not an option. It's not a nice to have. It's really mandatory. It's it's a must, and the demand will be really huge in order to fulfill the climate target. You see here some numbers that we found in the literature. That's necessary to achieve the targets. And the higher the targets, the higher is the demand for the specific products. Here's some example of work. So we work also on the lab level, of course. And this is a profile of a reactor that's this reactor is facing changing conditions. Of course, when you do a power to X value chain and process and this is related to the content of today. If it is a stationary process and you have fluctuations in front of a process, you need storage. And this storage is, of course, expensive and costs money. And you would like to reduce the amount of effort for this storage, of course. And the question was, the research question, is it possible to operate such a chemical plant also in a dynamic mode? And this is something we investigated in such a reactor where we applied changes in the concentration. In this case, it's a methanol synthesis, and you change the CO2 hydrogen ratio, and the more CO you have, the more exothermic it is, and the higher the temperature. Just as an example for our work, and you see the measurements and also the simulation, and this is something we work on in order to scale this process to industrial scale and to reduce costs in the end. That's for my side. Here's a picture of the Black Forest where we had a little seminar. So happy to discuss with you. Thank you very much.
Thank you very much. And I would like to hand it over now to Santanu to introduce the next two speakers or the presentations. Santanu, please.
Achim, if you could stop sharing presentation, that would be good.
Yes.
And I think one very interesting point is that we already started to got really some great questions, and so it's already building up. So please, Jihong, if you could introduce yourself to the people and go forward. Thank you.
I just share my screen. So can you see it? Okay.
Yes.
Right. Okay.
Thank you.
Right. I'm Jihong Wong. I'm the professor in electrical power and control engineering. Thanks IOP and DPG to organize this event, so I can share this recent development in compressed air energy storage technology. Okay. So why we need longer duration energy storage technology? And so this is from 28 independent study, and when we increase our renewable energy, for example, from wind or solar, and so that means we have a more intermittent and unpredictable energy power generation into the grid. So we need a more energy storage in terms capacity. So no matter it's from Great Britain, Germany, or Europe, or United States, other countries, although the studies may have based on different hypotheses, so the study may don't have identical results, but the trend is the same. And when percentage of renewable energy integration increase, the energy capacity, energy storage capacity will increase as well. And apart from the capacity, also storage duration also needed. And when they have a higher percentage of renewable energy, and the duration of the energy storage requirement will increase as well. So that means, and we need to guarantee we still have electric power if they don't have a wind in consecutive few days. And to come to the energy storage technology, there are various technologies, and this axis represents the power rating, and that axis representing time scale for operations responses. And to achieve net zero, to deep decarbonize our power grid, various technology and are needed. So here in my talk, I just concentrate on one technology, compressed air energy storage. And on this graph, the roughly compressed air energy storage is in this region. And probably we can see is suitable for large scale, but with a relatively slower response compared with the battery or capacitors. And then come to the cost, current cost. And that's the range of cost from various published literature and also some demonstration plants. And so in terms of energy capital cost and also the power capacity capital cost and compressed air energy storage, and is relatively lower than other technology. So I have been working on this technology since 2005. And what is compressed air energy storage? And the process is relatively from physics, it's simple. And during off-peak, when we generate excess electricity, we use electricity, drive the electric motor and the compressor to compress air stored in the kind of reservoir or a container. And when we need more electricity, we just release the pressurized air and to power the turbine or expander to drive a generator to generate electricity back to grid. So the charging process and the discharging process. And that's a compressed air energy storage technology is not new. And very first power plant was built in 1978 in Germany. That's is power grid and energy storage capacity as well. So, and in this plant, the compressed air stored in underground salt caverns, because you can get a large volume of storage as compressed air energy storage has a low energy density. And in the process is involved natural gas to boost power during the discharging process. And the second one built in 1991 in America, similarly, and use natural gas as well. But this plant has a high efficiency because it recycle exhaust heat. And the current effort in terms of technology development and the research is trying to work on the plant process without using any fossil fuel, get rid of the fossil fuel. So trying to store the air, heat generated from compression process and reuse during the expansion process to increase the round trip efficiency. That's probably the effort currently. And as a need for the longer duration energy storage or large scale energy storage to decarbonize the power grid. And this technology has been relatively active over the past 10 years. And that's some list of demonstration projects. And you can read this reference. Certainly that's 2021 publications. And now there are more demonstration of the project and start should be added onto the list. And the main message I would like to share with you is about the technology development in recent years. In 1970s, the first power plant only got 46% energy efficiency, round trip efficiency. And 1990s is over 50 plus kind of efficiency, all of them using fossil fuel. In 2019, the 10 megawatts A case power plant and in commissioned and generated electricity and been connected with the grid. So the tested efficiency is over 60%. And this year, there's another demonstration plant, 100 megawatts, and already did a partially test and is expected the energy efficiency will go over 70%. And certainly the cost of this technology gradually and decrease. I'm not sure the trend will continue decrease, but definitely cheaper than 20 years ago. So that's my final slides, and thank you very much. And that's my email. If you want to contact me, you can use this email. Thank you.
Thank you very much, Jihong.
I just
yeah, it was.
Yeah, stop sharing.
Yeah, perfect. Thank you. It was short and crisp, and it shows how important that air storage, compressed air storage, energy storage capacity is, or that has the capacity and the cost is low. And now let's go to our final panelist, Dr. Ulf-Peter Apfel, and if you could please present, say something about the work. And we know that you are the last minute addition, so thank you very much for that again.
Yeah,
so,
thanks a lot for having me here, and apologize for not having such a nice slideshow because I just was informed yesterday evening to join this this nice group here. But I think I don't have to add a big slideshow because a lot of things were already shown. So just to introduce myself, Ulf Apfel, I have the privilege to work at the university and also at the Fraunhofer Society, more or less connecting basic research and application-driven research. And I think this is a wonderful experience also in the field I'm working in, which is mainly electrocatalysis, to connect the dots, because this is these are partially new technologies that needs to be developed. And this is not only on the basis of, I'm an inorganic chemist, this is not only on the basis making a new catalyst, but you experience very often you have to craft that into electrodes. You have to make really sophisticated electrode structures. I think Nick can agree on that a lot. And then you have to bring that into the right reaction engineering. So rather than what Nick is doing, working on the on the solid oxide materials, we're working on low temperature membrane cells that are mainly operated for use it or for converting protons to water to hydrogen, or reducing CO2 to give you, for example, syngas. This is something we're currently building up a 50 kilowatt pilot plant for making this directly, utilizing exhaust streams from, for example, concrete plants, or even electrifying chemical industry. Think about hydrogenations. This is a classical chemical reaction. I think you all had at least a product of this on the table today. Margarine, the synthetic butter. This is a product for hydrogen, made from hydrogen. So what we're doing, for example, is we're not using hydrogen, we're using pure water and electrons. And you need to have the technology ready to do that in one step. And I think there are a lot of things that already are quite advanced, but there are a lot of things that are at a very early stage and not very efficient at the moment. And I think in terms of what is the technology that needs to be developed for long-term energy storage, I think that was very nicely shown by Jihong. It's not a single technology, I think. It's a bouquet of very different technologies for different kinds of applications. And one of the critical things that I always encounter when talking to industry partners, a lot of people have no idea what they want at their location. Because a lot of things are not known. It's not like going to the big power plants or going to the big chemical plants where you say, I want to have something similar that works like this, and I want to have this and this and this parameter working at this operational costs, working at this capital invest costs. This is not present for a lot of new power to X technologies. So in my mind, it's really about developing a lot of different technologies and using them at best where it fits best. It's not a single technology, but I think it's a bouquet. And I'm really much looking now for the discussion on the various things. And that's more or less everything I had to sum up of the speakers before, that is nicely connecting. And probably one last word just to say it's not like the old chemistry is out now. I mean, for example, chemistry like Achim Schaadt with the thermal catalysis is very important, but then you have to talk about connections, connecting the classical pathways with new technologies, where you step in, where do you feed in the electricity. In the future, my personal belief is electricity is nothing else than just a fossil fuel. It's just a kind of power, but you have to integrate this. So you have also to talk about sector coupling and so on and so forth. So I'm very happy to be here and looking forward to your questions.
Thank you so much. Thank you. It was really apt for this presentation and for panelists. And we as I said that we are expecting questions, and we have quite a few of questions already. But I would like to say, before you go to the questions, can I ask Netanya that will the recording be uploaded or published somewhere? Because that was one of the first questions that came. Will it be available somewhere or?
Yes, the recording will be on the IOP YouTube channel.
Oh, that is perfect. Thank you very much, Netanya. Okay, so now we have got quite a lot of questions, and earlier we decided that if we have a question that I got more thumbs up, then we'll go with those ones first. And we have one from David Croft already getting quite a lot of thumbs up. So the question is that, do the panel think that lithium-ion batteries attached to domestic solar panel installations are a good solution to energy storage? And is it sustainable to have so many batteries installed nationally? Please, if any of the panelists could jump in and start the
I can
discussion.
directly jump in because I just installed one in my own house. Yes and no. That's a simple answer. And why I'm saying yes and no. I would have loved to install a redox flow battery, which are already commercially available as well, but the cost is currently significantly higher to what you get for a lithium-ion battery. So I think if the technology would be a bit more mature in terms of pricing, I would definitely be in favor for such a thing, but it's always a matter of cost. So I think, yes, it is one technology that we have to keep on the list, lithium-ion batteries, even so with all the problems that are associated, like abundance of lithium or the recycling that has to come afterwards, which is still an issue. But I think then there will be more technologies also ready at hand for static use, like the redox flow. You can make them bigger and there is not an issue. Even so with the vanadium pricing, I totally agree with Nick that it's a bit an issue, but you can rent it nowadays. So you can rent vanadium electrolyte from big companies, and then it's not as expensive anymore as if you would buy it directly. So you can even go to the larger scale. And we also had a startup on that, which is now sold, the former company Voltarion, that built redox flow batteries, and it's commercially readily available. So it's a really mature technology nowadays that it's not big, you can use it, and it's quite unlimited power you can get.
I'd sort of have to agree with that. I mean, the way I look at lithium-ion batteries is quite different to other storage technologies like compressed air, like redox flow. Lithium-ion is very much, the more lithium-ion you add, the more power you get. So you're paying a lot for that extra power that you can't use. So in a home environment, connecting solar to lithium-ion is quite a nice, interesting idea, but it doesn't solve all the problems associated with decarbonisation. And I think what we're talking about here in the panel, in some respects, is how do we manage resource adequacy? How do we count for the days when there is no sunshine, when there is no wind? And how do we manage that? Because that requires huge amounts of energy storage. And I don't think everyone in a domestic environment is going to be able to achieve that. So absolutely, lithium ions are a great solution for certain elements of the energy storage chain. And they're already being deployed at scale for cars and also for stabilizing the grid too, which is a really important, that's where lithium ion works really well. But because you can't decouple storage duration from power, it becomes harder and very costly to store at a much longer durations. And as a result of that, the other technology is talking about, like redox flow, where effectively you can say, if I want a longer duration, I'll have a larger volume of electrolyte. It works very well. Same with compressed air. You can have a larger cavern and you can store more power. Lots of these other technologies, hydropower, everything else like that, they're all able to decouple power and storage duration. And those are the sorts of technologies we actually need to bring forward and come through now to solve and get scale at pace for deep decarbonisation.
Sorry, Carl, please.
Many thanks, Nick, for that clarification. I just want to jump in with a remark which guide us for the next question, because you have already partly given the answer. The next question is long-term and huge energy storage. Which system looks promising? I would like to add a remark, because you and other ones have already used the word decarbonization. And if we take this seriously, then we exclude a lot of carbon-based synthetic energy storage capacities. So what we really mean is, and that's a way of wording, what we really need is a defossilization and not a decarbonization, because carbon is our environment, carbon is our organic life and world and so on. So I'm always fighting for that wording, and Santanu knows it, because I always use any opportunity to point out. But I agree what we do, for example, in our big research programs, also in Germany, we have a future carbon cycle as a headline for the future. So that means carbon, which is already available in the atmosphere or in the biosphere, can be reduced by using renewable energy or renewable or green electricity, and then we can do let me say a synthetic climate neutral hydrocarbon producing, because hydrocarbons have a bigger energy storage capacity than only hydrogen. So that is just a remark from my side. I think if one of you would already jump into the next question, which systems look promising? It's Günther who has raised the question, which systems look promising, at what time and what price and time scale? Who wants to jump in?
I don't think I can answer this question fully, but I can show you an example from, I think to save time, I didn't show this slides. And probably you can say that's one study we did. We used 2018 UK power generation data. So that's the blue line is the demand, how much electricity we need. And the red line is how much natural gas we use for power generation. Green is from renewable energy. It means wind or solar. So we start thinking, and if we use without any long-term energy storage, if we just increase of renewable energy and to meet our demand. And so that's, we cannot really get rid of gas, fossil fuel. So the peak, if you look at this power rating, almost the same. So now we did a kind of study, just because in the UK, natural gas now stored in this underground salt cavern. We supposed to replace all this natural gas with compressed air, and but still have some other, gas power plant. So with that, that's the suppose we analyzed the 13 sites in the UK. So that's what we studied. Even longest storage duration is 96 hours, and that's how many cycle time that's per year you need to charge and discharge to meet the balance. But we can cannot get rid of phase out all the fossil fuel. We still need a gas power plant. So that means single technology wouldn't be able to solve the problem. We still need a longer than this duration of storage. It's not the firm answer. Everything is still unstudied, but at least this example tells, and we do need various technologies. Yeah.
Probably I can add up a little bit on that. I would say there is not the one technology that comes up. There are several technologies that are at hand and that needs to be used. I'm not a big fan of reducing CO2 like Karl-Friedrich mentioned, and making fuels out of it. I'm not a big fan, because then it's easier just to use the fossil fuels and to drive with them directly. It's more energy efficient and less polluting, I think, in the long term. But I think you have to think about thoroughly, what do you mean by energy storage? And I think energy storage is a very versatile word, because it includes its use as not only as a power source, but it also includes its use as something that you can make chemicals out of it, high value chemicals that are energy rich materials. And I think you also have to include that one. So it depends on the application you want to go and what you want to exactly do with that. In a lot of scenarios, you're talking about hydrogen as the fundamental basis of energy storage. If you try to count it up and summarize the production capacities of making new electrolyzers, you will recognize that, especially also in Europe, we're talking about 40 gigawatts until 2030 that's supposed to be installed. We currently even don't have the capacity worldwide just to come close to that level. That's why we have also this big research plans in Germany as well, for doing an automatization of electrolyzer technology, but we are not there yet. So at the moment, it's big fantasy. With that big fantasy, if you would have the elaborated technique, for example, now to make PEM cells in such a sophisticated manner, then it's a question about platinum abundancy, iridium abundancy. If you lower one, then the other one is not easily available anymore. If you do a recycling for platinum, or that's not good for the iridium, because then it's not digged out of the earth, because it's a byproduct of platinum. So it won't be the case anymore. So it will get even more important and more expensive. So I think there's not a general answer to that question. This is very difficult. And I think there needs to be the multiple technologies that need to be ready at hand, just to have this bouquet in giving you the chance just to not only rely on one, because this is the big issue, what we also have in Germany, relying on Russian gas fed. So we should not enter this streamline and rely on one single technology. That's not good.
I totally agree with that. I was going to say we need it all in some respects, because the challenge is so great. You know, if you look at, I think Jihong had some predictions, but I've seen others too, where we're going to need, you know, between 85 and 140 terawatt hours of storage by 2040. And if you just take one example of a good long duration storage technology, which I think has an opportunity to scale too, which is pumped hydropower. If we look at an example in the UK where we've got Warwick that stores 9 gigawatt hours, if we need that 85 to 140 terawatt hours of storage, and we just went to pump hydro, we would need 9,000 to 15,000 Warwicks. And that's just going to be really hard. So, you know, we're just thinking about the scale, but also thinking about the resources that we've got available to us is really challenging here. And, you know, to pick up on another point that Ulf made too, is very much, this is a materials limited play too, in some respects. Some of our materials are limited. You know, we're looking at how lithium ion has scaled and how we're going to be using lithium ion maybe for electric vehicles, and potential scarcity, well, not scarcity, but the need to ramp up production of lithium ion with all of these other chemistries too. There is a scale question around them. So you know, some of the huge energy storage technologies will be the ones that have access to abundant materials that can go at scale.
Yes, and I'd like to make one point, as Dr. Apfel said, and it's all a bouquet of techniques. And also very relevant is David Croft's comment on the lithium-ion batteries connected with the solar power. And it could be quite a good option for the countries where lots of sun is there, like, and throughout the year, like in some of the African countries or some of the Middle Eastern or some South American countries. So it, as I say, that it may not solve everywhere in the world, but some places a solar powered lithium ion storage kind of thing, a combination of that could give a good alternative until we have a complete green solution. And also lithium ion, the scarcity of those things that you just, Nick, highlighted.
Yeah, I might add up on that. Sorry, Nick, I might add up on that directly, because I was recently in an Arabic country where they have a lot of sun. sun is shining more or less all the days, but they have another issue. They don't have the water. So, I mean, if they want to use the electricity just to make hydrogen, they're a bit screwed, honestly, because they don't have the water. They don't even have the drinking water enough. So they would have to do a desalination. If you don't have access to the sea, then you have different things. Even so, if you would have the access to the sea, then you might encounter different options with a lot of salt increase in the oceans or in the near environment. You also have to think about that, because then we're not talking about just the drinking water you have to generate. We're talking about significantly higher numbers in water that you need. And that might cause an issue.
Absolutely.
Yeah, I agree, and it points to something that I've learned, which is that the solution or the mix of solutions in different countries will be different, because each country's solution to defossilization will be different depending on the resources they have available. So absolutely, in places where there is a lot of solar, then storage technologies that work on a sort of daily charge discharge basis can work really well. In other countries where maybe there's more wind, UK is a good example where there's huge amounts of wind. We're doing really well on producing wind turbines. We've got 25 gigawatts, I think, installed now, and that produces 25% of our overall power needs. It's a very different cycle, and it needs a different mix of technologies to match with it. And there are different opportunities because of that.
And this readily answers actually Chris and Jane's question that it is always sunny somewhere in the world, it is always windy somewhere in the world. So is it worldwide grid a feasible option? We are having that energy grid from wind power already in different countries, but the question is that whether it is possible. But I think that is more going towards political, like the laws of different countries.
I think it's not political, because this is actually what China is currently setting up in the world. I mean, if you take a look at their politics, they're setting up photovoltaics units in South America. So they're planning for the future, and as they really see it as a global challenge. Where, as Nick said, the things are distributed around the world. So, and I think if you do it I mean, Germany is doing it heavily. They always think in autarky. I don't like this word at all, because it means like independent from everything else. That never went well, and it doesn't work. So you have to think, I think, more in networks and in more global.
Yeah, cross-continent, cross-country, cross-continent. Connections, high voltage DC lines, they can be made to work. Good example is the Norway interconnector in the UK that went online recently, that allows us to have access to pumped storage and pumped hydropower from Norway. It's a brilliant concept, and we need more of that.
We have another specific question for directly to Nick, is that it's about your technology, and it has got quite a number of votes. The technologies you present look promising. What is currently hindering us to implement on large scale?
I think to implement on large scale, that there is two things we need to get over the line. Firstly, as I'm sure you're aware, we are working with many partners who want to make our cells and stacks at scale, and we need to get those factories up and line and running. But we will, within a very short period of time, have factories in Korea, in Germany, and in China too. So the scale is coming, and I think in addition to that, and if you think where Ceres has been in the past, we did start with quite small scale stacks and systems, and we need to have the right partners around making these bigger high power systems, and we need to do the right engineering work around that. And that's part of what we're doing with the 1 megawatt demonstrator, for an electrolyzer, and other partnerships we've got, maybe in marine and other areas.
There is another question, and I think we should move forward to other questions. One of the big issues is, how can we store a huge amount of electricity or energy? I would like to point out we have two questions. One is a storage option, and the other one is a transportation option. So When we store it locally, the electricity, we use it locally again. When we want to transport it on a global scale, we have to put it in a version, in a modification that can be transported. So I pick up the question of Jürgen Pennings. He said, to my opinion, a really big amount of energy is at the moment not a chemical way, he is asking, or a statement, but storing it, for example, in a pump storage lake, and there are limitations for pump storage. The other huge possibility is compressed air, which you have already explained. So who wants to jump in just to answer the question, what is about pump storage lakes? I know there are a lot of ideas on the table, but always conflicting with natural protection, with the problem of which valley, which mountain is available for pump storage. Is there any
Actually, this is not the biggest problem. I mean, in Germany, we don't have the problem that they're not there. I mean, current pump storage systems are getting even shut down because there is no profit. So they have to pay twice. So they have to pay for the price for the energy they use for pumping the water up, and then they have to pay the price again, taxes for making the electricity. So it's double cost. So it's not very lucrative in that way, and I think it's a political thing that there needs to be some regulations. At the moment, in Germany, we are selling a lot of this energy, excess energy, if you want to say it, even so it doesn't really exist. If we sell it to Austria, and they have the business model, the Germans are paying for pumping the water up, and they're paying again for buying for getting the power again. I like that model significantly more because it's not taxes, it's paying the price. But unfortunately, it's not the way that it's done in Germany. But I think it's not a matter if you have a storage lake or if you have a gas pump or whatever you need. It's a matter of when do you need this electricity. And I think Jihong and Nick already said something about that. It's a matter of time. You can't anticipate that when the current is breaking down and you have a pump storage up there, within the next few seconds you have the power again. That doesn't work. There, for example, their lithium-ion batteries are quite okay. But for a steady state current, I think that's a pretty good strategy to go with.
Yeah, I mean, it's very clear that type of technology would be good for storing large amounts of power. I suppose there's a question over all of these technologies in some ways is how do you make them sufficiently cheap that they are a good economically viable proposition for an energy company to effectively buy and install. So if you take the example of de Noray, that was actually built in, I think, before the year 2000. I think it was maybe even the 70s, and it was built when the UK government owned the energy infrastructure in the UK. It wouldn't have been built nowadays. Now, the reason is because you couldn't make a significant enough return on the investment for that pumped storage hydro site. And in fact, interestingly, de Noray itself, although it is a long duration storage technology site, it makes most of its money selling frequency response services to the grid at the moment, which is quite a challenge because in some respects we all can see that you need energy storage, but we've got to find a good way of valuing it so that we can actually scale some of these technologies.
Mm-hmm.
So just follow Nick's and understand it's a market. And probably every country you see the biggest growth in recent years is a battery energy storage. And because the battery energy storage serves in the fast response market, that value quite high. But if you invest onto, for example, compressed energy storage, even technologies cost less, but come to the market worth much less, you still cannot get your investment return. And another barrier is for any larger scale energy storage, you have a big risk to take for any investors. So that's if the market is not there, and for probably difficult to attract investment into it. But for battery storage, you can go small scale, large scale, and also market is really ready for them. Yeah, so they can make money, and
yeah,
so that's another cost
totally
aspect. Yeah, the value in the market is another aspect.
The market is there, and the UK has got one of the most developed markets for valuing the benefit to the grid of lithium-ion storage, with various grid service mechanisms, and there's been huge and rapid scale as a result of that.
And I believe we also have our new energy storage policy coming in 2024 government, so that might give us some help to the companies and the people working on that, and some funding for that. And I think one very important point Karl highlighted was the transportation, and we have one question that is connected to very by Dr. Ingo Borz. And if I read it, we do not only have a storage challenge, but also an energy distribution issue. What advantages do the different storage technologies provide in terms of transportation? This is very important, is that we don't only have to have the stored energy, but we have to transport it in a number of cases. Like we store a lot of energy in Australia, we need to transfer it to somewhere where it's needed. So those kind of situations. So transportation become very important and vital. So if any of the panelists could like to jump in.
Maybe I can jump in this point. So I think transportation is especially interesting for this hydrogen-based carriers, which can easily be liquefied, such as ammonia. We have currently, of course, a really hot discussion about ammonia, as hydrogen is not so easily being transported. You can, of course, liquefy hydrogen, but there's only one ship available, one quite small ship that can transport hydrogen, but not that huge amount that would be needed. That's why people think about going even further from hydrogen to ammonia, of course, with all the consequences that you might face regarding toxicity and corrosivity and all this issue. But in principle, the issues regarding transportation are solved, and you can really effectively transport huge amounts of energy in form of ammonia, and this makes it quite attractive, as you don't need any CO2. So this is something typically I agree with that what has been said, that you wouldn't go without need further than hydrogen, or ideally you would stay with the electricity, but sometimes you need the transportation, and then you have to go forward to hydrogen, or even further to ammonia, or maybe methanol or methanol-based energy carriers. But this depends really on the amount that's needed, and on the application, and on many issues.
Let me just add a remark on that, Achim. I share your opinion. The question is, which form of chemical energy carrier shall we choose for a long range transportation? Not only, as Ulf said, as a fuel for car, I mean just for energy transportation. And I remember last year a very nice let me say, marketing headline issued by the Australian government when there was a memorandum signed between Germany and Australia to produce renewable electricity in Australia, and then producing hydrogen or producing derivatives of hydrogen. And the Australian government immediately published a press release with the headline, "We are shipping the sun to Germany." So that is the content of this discussion. I think we have to favor, and Ulf, I agree, we will have the need to import solar energy in various forms from all over the world to Germany. We will have, let me say, no autarky in Germany on that issue. That's quite clear.
Yes, I totally agree. I think it's not an issue, but maybe Ulf, you want to reply.
Yeah, I definitely want to reply, because I mean, what you ask, Karl, is more or less like taking a look in the glass bowl. Who has the right answer? Which is the transport molecule that is reasonable to go? There are some good sides and downsides for hydrogen, which is, I mean, the volumetric energy density of hydrogen is, let's don't talk about it. The mass energy density is pretty superior. But then you need these big container ships, you need to compress it, that costs energy and so on and so forth. There are some nice calculations when it makes sense just to put the H2 in the pipeline, until what kind of amount of kilometers it makes sense, when to ship it, and so on and so forth. So this needs to be calculated.
Sure.
I would always say never trust the statistics you didn't fake by your own in that way. It's very complicated, because it's a lot of data driven, but there are not a lot of reliable data available currently on how to do that exactly, because the market is not, I mean, the net is not there. And for the oil stuff, we have currently, we building up, or we generating the data after we already erected the entire system. So it's a different matter. In terms of ammonia, I see a different problem also forthcoming. I mean, ammonia is not there just as an energy carrier. It's used to make fertilizers and all kinds of different chemicals. When you're producing fertilizers in countries where you currently have a lot of sun and the electricity ready to go, these are usually the country that buy the fertilizers from Europe, from Russia, from North America for a really, really high price, sometimes about 10 times as much as you pay in Germany for this for the fertilizer. So my question is, why should they ship it back? So this is also, I mean, the distribution problem we're talking about now in terms of energy distribution also fires back in terms of these things can be used for something else. And then we have a distribution problem also in the other direction, namely using it as a fundamental basic chemical for chemical industry. So I think this is the thing which is not a one-way discussion on how to transport it and to distribute it only as an energy distributor, but I think we have to discuss about how are the streams, and I think we have to think globally again here.
Yes,
I've got a personal opinion on that, and you're absolutely right that you look at the numbers and there are different statistics and this, that, and the other. But in most cases, if you need to store the energy and then transport it somewhere else, you're going to need to consume more energy to convert it into something that's transportable. So we know that gaseous hydrogen is difficult to transport because it's low energy density. But if you convert it to ammonia or methanol, there's another energy hit to do that. And then you're consuming energy to transport it, to get it to where you want to consume it. You have to be careful that you don't consume a lot of that energy in the process to get it to where you want to use it. And then when you're at that place, you need to then convert it back into something potentially that's electricity. And I think you'll find when you do the maths on that it's actually quite a low round trip efficiency if we talk about energy storage.
I suggest that we continue a bit with some of the questions. I have seen a question of Hardo Bruns, for example, on compressed air. That is for you, Jihong. The question is about compressed air storage with 4 gigawatt power level. What is the view on scaling this to this level?
Okay, so I think the compressed air energy storage for generation, for discharging process is quite similar current turbine technology and gas turbine. So if you go to the current thermal power plant, they all have a parallel power generators and turbines working together. It's not like a single generator or single turbine working there. So for compressed air energy storage, the same. If you have a few hundred megawatt scales, you put into the same plant or same site working in parallel, you can scale up. So currently there's a new project in the design stage to scale up the 100 megawatts demonstration project into 300 megawatts as so I think that's probably the solution to that.
Okay, thank you. The other question is a more, let me say, general question to all of you. How is Marcel Lauterbach, how realistic is it that we can store in the near future enough energy to base national energy production entirely on renewable, but highly fluctuating sources? What will be needed to make it happen?
So maybe I can start. So we did some calculations at Fraunhofer about the energy system. It's a model called WEMOD. So the idea was really to have an idea what would be the pathway to a cost-optimized pathway to a renewable energy system, really based on renewables, and in this case PV and wind energy. And of course, the result was positive. That's important to go forward. And it's a mix what's needed, what's already discussed here. It's of course, a lot of batteries are needed, electrolyzers are needed, but also gas turbines are needed. And with this mix that was already discussed of wind and PV, it determines in a way the amount of storage what's needed. That's really important. And of course, you have to consider imports as well. So it's a really complex modeling approach. If you change one thing, you change a lot. So, but the positive message is it's possible. And but we have to think about really the speed. How can we apply and ramp up the solutions that are available? I think that's important in general.
I saw Ulf agreeing. Would you comment on that?
Yeah, I absolutely agree on that. And we had several discussions also Fraunhofer internally already on these issues. The thing is, what we need for doing this is, as Achim pointed out, we need the technology, and not only a single one, but there needs to be several ones that actually cover these aspects and allow you actually to generate this mix that Achim was talking about, that you're not rely on one single thing. Because if one is skipping out by any chance, that let's say you have 1 year no light, which is unreasonable, but let's assume this, then you need to cover this, and you need the techniques just to do this. And I think if you have 20 different technologies ready at hand that you feed into the system, you will be fine. And this is possible. But the thing is, you need to have the push from society, from industry, from politics, just to establish that, because we have a little bit a hen and egg problem. What do we start first? There is no market currently for that, for a lot of things that needs to be built. But if there's nothing that is in upfront as technology, then there will be no market. And so it needs to be somehow, there needs to be some incentives.
Or incentives or regulatory, it needs a regulatory framework that makes this system attractive. That might be incentives, but of course, with this tool, we have to be careful. But currently, there are a lot of incentives for fossil fuels in the market. And if you reduce that and shift, then it would push, of course, for renewables as well. So the regulatory framework is one challenge I see, and one big drawback for the ramp up. And I think as the technology moves quite fast forward, the regulatory framework is not that far, not that developed as needed currently. And this hinders the development and the deployment of new technologies, in my opinion.
I would give this remark just to our UK colleagues here in what do you think about regulatory framework? Because that's usually a problem. If you do it on the national basis, you will, let me say, hinder your economy to develop in competition to other countries, to other regions of this world. How do you think in UK about that?
It's an interesting question. I'm not fully up to speed with the very latest UK view on this, but I think it comes back to what I said a little bit earlier, that we in the UK, we know we want this technology, but we have not found a really good way of valuing it yet. It's not to say that we're not looking at it. That's not correct. I know National Grid are looking at it, and the government is too. So there isn't a strong regulatory support in the UK for technologies outside of lithium ion at the moment.
And if I may add, is that this is very important for us, and the government support and the regulatory support that we need, it's not there yet, because very surprisingly we had £7 million available for research, which is really nothing. Whereas, and that's why we are very much looking forward to this 2024. That is a big changes in the energy. So there is a government law or something coming out of that energy storage thing, and maybe that will support us a lot in help us in that direction. And the reason we may not have this, because of in last few years we haven't had that had a stable government, and that's why maybe things like these things went to behind rather than coming in front and being resolved earlier. That's absolutely my opinion. Jihong, if you'd like to add something.
Yes.
Yeah, I think UK compared with Germany, I think our electricity market is electric power system is more market driven than Germany, and so our electricity market is rather complicated, and many kind of products and for people to play, and I think that's a good thing, but maybe another thing is become overcomplicated and difficult to bring all the technology in and value them. But I think this current digitizing the energy system may help in the future to realize various kind of mechanism strategy to recognize the contribution to make it to get the true values of various technology.
So I conclude from your remarks, we have a, let me say, situation, regulatory framework on one side and successful business cases on the other side. And I learned from Ulf, for example, that some of the, for example, the pump storage technologies are no longer a successful business case. And as at least that was your remark.
I would not say this for general. There are some issues associated. It could be a very successful business case.
I know something about our Black Forest pump storage lakes and the utilities operating it, and I know there are several reasons why they don't proceed with that. So, but in general, yes, this is one of the options, and I would like to look again in our questions. We have only a few minutes left, so if you agree, Santanu, I select just one maybe last question from Gunnar Rode. What is about the sustainability factor? Does it make sense if we ship green hydrogens to the EU with a lot of losses when it comes from countries that are not fossil-free at all themselves? We discussed or touched already this question a bit, but I would say, I would, let me say, extend this question. What is about the sustainability factor as such on long-term storage technologies? Who would like to jump in?
Maybe I start, as we have really LCA as an important topic at our institute, and it's important, and there are a lot of work currently running regarding sustainability of hydrogen as such. So of course it's discussed about the colors, but the tendency is that the low carbon footprint is essential, not really the color. So I think now it's the discussion about the details, but this has to be fixed as soon as possible, because this is needed in order that investors start and that the business can develop. When there are decisions made, then really the investors know how to deal with it. But if it's not clear, then nobody will start it. So it's an important point, and it will define in the end the business cases.
Mm-hmm. And maybe I add just another final question, which I just see here. Friedrich Wagner asked, how much wind and PV energy can be generated in Germany in 2045, given the installation potential? How much hydrogen can Germany produce in addition to the electricity generation? That is one of the crucial questions. We all see a huge demand on hydrogen, but if you calculate it, you see that the potential to produce hydrogen in Germany, Ulf, I'm looking on your side, for example, you mentioned that our autarky is limited. Would you respond to that?
I think Achim is the better person to answer at least how much PV can be generated, because I think ISE has some studies on that. There I'm a little bit empty-handed, but at least on the hydrogen that can be generated, it's definitely there are some forecasts that we can probably produce 25 to 50% of the hydrogen that we need in Germany. At the current level, we can produce it by our own. The rest has to come from outside. And this is mainly for the industry. We're not talking about mobility at the moment a lot, because it's only anticipated to play a major role for mobility like trucks or trains, but not on the small scale mobility for cars. But industry requires a lot already at the moment. So I would say we are definitely in Germany, we are in an import-oriented country. We will stay this because we don't have the energy resources, I think, at hand to do it from our own. But that's okay. I think it's more or less a matter on, we can connect it also with a sustainability question. It's a matter on if we want to continue running the thing like it is nowadays, or if we want to invest a lot and make significant changes to change the entire system, which also demands that some of the certain industry parts will move out of Germany or move somewhere else. But all the statistics I see, all the forecast is not that industry will really move out. Also the heavy industry, like the steel industry, they're currently trying to set up their entire facilities for hydrogen in the future. So it might stay here. And the pricing is not significantly more expensive than what it is now. It's probably a factor of 1.5 in price, which is not tremendous. If we're talking about general energy increasing prices of about 1.5 to 2.5 or something like this, this is a factor, or these are factors that I constantly hear from industry partners that they anticipate. Then I would say this is not the limiting fact. About the PV, Achim, do you have numbers on that?
I have some numbers, so that I think until 2050, I think more or less a factor of 5 to 7 fold of that has been installed currently has to be installed in order to fulfill the target. So it's a huge amount. So in the end, more or less about 500 gigawatt or something in this range, it might be possible, but it depends, as I said, on the mix of PV and wind. But how is that realistic? So of course it's a big discussion about that, but what we see a lot of potential when you think about integration into buildings, not only the roofs, but also integration into the buildings, into the vehicles. agro photovoltaics along of the highways. You can build PV. We will have a project where we have a roof for bike way. So there's a lot of possibilities for space that has not been used before. But it's a huge task, of course.
So yeah, I think Karl, for considering the time, unfortunately, we do have to stop at some point, and I'm really thrilled with kind of discussions, and there are so many good questions that we couldn't answer, something to do with biomass and the green hydrogen and sodium-ion batteries and so on. So sorry that we couldn't get into all those questions, and I would be really more than happy, because you have the email address of all the panelists and everyone here. So if you could please write to anyone you like and raise the question directly to them, they would be more than happy. And Karl, it's now up to you, please.
Thank you, Santanu. It was just my intention also to stop the discussion right now. I always feel a bit uncomfortable if such a lively discussion has to be stopped. And we have had now 1.5 hours. I thank you, the panelists, very much. I think this was, at least from my point of view, it was a very good discussion. It was very interesting. We did not come out with the one solution. I pick up the message we need to all options for long storage technologies. The basic question is sustainable point of view, environmental point of view, but also business case point of view. If there is not an investor willing to invest, we will not have a solution. The global aspects have to be regarded. We have discussed it, and we have discussed also the regulatory framework, which probably is necessary. Natanya reminds us in the chat there is a poll now going on. First of all, we have a feedback poll, which I invite you to fill in. All the audience, please jump in. You will help us to improve our meetings in the future. Please give your answer. There is also the possibility to propose or to vote. What shall we discuss next time? I mean, this is a series of events between the British IOP and the German DPG. And we would like to know, what is your favorite topic for the next time? Even there, we have the possibility, or we have announced some topics, and you can, I don't know exactly, Natanya, where we find these topics, but where to stick in and say, here, this is a topic which I would like to have for the next time. A suggestion in the chat box, the chat box, okay, about what topic you would like to see in the next meeting. And with that, from my point of view, again, there's only a big thank you, especially also for Ulf, who jumped in today. So I really appreciate what you did today. My special thank you goes to all others in the preparatory team, and the final word is going to Santanu. Thank you also personally. It was an excellent cooperation between two of us, and we had a wonderful preparatory time. Thank you. And Santanu, you have the final remark.
Oh, thank you very much. Thank you, Karl. It has been really pleasure, and thank you. I would like to thank all the people actually who attended this conference, these discussions, and raised those all exciting questions, and which we couldn't actually answer or give our opinion on it. So really sorry, but thank you so much for being here and attending this course. And thank you, panelists, as Karl already did. And I would like to, and I think we all of us would like to thank Natanya very much. Without her, this whole session wouldn't have happened. So thank you so much, Natanya. And finally, to the IOP and DPG organizers and rest of the team and everyone, thank you so much. And we would look forward to your opinion and feedback and things and topics that you would like us to discuss in the next session, and we would continue to discuss further. And the collaboration between DPG and IOP is really a panel or place where we can bring our opinion together and widen our knowledge. So thank you so much, everyone, panelists and the people who attended. Thank you.
Thank you.
Cool.
Okay.
Bye-bye.
Bye.
Bye. Thank you.
Bye.